All right, so this chapter is called Chemical Reactions, and we're going to explore how chemical reactions occur and balancing chemical reactions and identifying the kinds of chemical reactions. So, the first thing you need to understand is why chemical reactions occur. Chemical reactions will occur because there are molecules or atoms that need to collide, and the collisions among these atoms will allow them to become different things. There's a couple things that need to happen in that regard. You need to have the proper, what we say, orientation. So if you have like a water molecule that needs to combine with something, maybe it's that oxygen that needs to react. So if it's going to hit some other atom or molecule, oops. Um, so let's just say this is some molecule that it wants to hit. Maybe the oxygen has to be the one that's doing the hitting and not the hydrogen. So the orientation of the collision is important insofar as how hard it's hitting. So that's sort of what's being described here. They have to be fast moving enough. They have to be in the proper orientation. So some things that can help are temperature, concentration, and surface area. So let's take a look here at some situations. So here I got two types of molecules in this container. And if I were to heat them up, what would happen to their collisions? Now, hopefully you remember when you heat things up, they move faster. So moving faster would lead to more collisions, and then cooling them off would slow them down and lead to fewer collisions. So that's going to affect how the reaction goes if you heat something up or cool something down. The other thing you can do is add more atoms or molecules so that they're more likely to collide, right? As the concentration increases, now it's hard for two things not to run into each other. Likewise, if I release and the concentration is very low, now it's harder for things to run into each other. So these are some things that you can do to dictate how the reaction occurs. So you can increase or decrease the number of collisions based on temperature. With concentration, you can increase or decrease the number of collisions. And surface area. Think about how if I put a block of something, the stuff on the right in the middle of the block can't be exposed. The only thing that's exposed to a reaction is the outside. Whereas if I grind that up into a fine powder, now I've got much more surface area, much more ability for everything to react at once. So surface area, and that's actually, if you think about it, why we chew our food. We want to increase the surface area of that food so that it can be digested by your body. So there's certain driving forces that will make a reaction go forward. Formation of a gas is one of them. Formation of a precipitate, which is a fancy chemistry word for solid, and formation of water. If you make water, um, that's going to be a driving force. And we'll get into that a little bit later here. Some symbols that we have when you're looking at chemical reactions, if you see an S in parentheses, that lets you know that the substance you're looking at is solid. This could be helpful if you're following a reaction and you don't know what state of matter the reactants need to be in. Were they dissolved? Were they solid? So this is telling you basically, is it a solid? Is it a liquid? I'll try to use this cursive L because a lot of people think the other L is an I or a 1 or something. So I'll try to use a cursive L for liquid. A lowercase g is gas. AQ stands for aqueous. That's the actual word. But what it means is dissolved in water. You can write aqua. You can kind of see that root there. Adding things. So if you have hydrogen plus oxygen makes water. The plus sign is what we use to mean you're adding a different chemical. If you have an arrow, that'll tell you which way the reaction's going and it yields that. If you have a reversible arrow, and it's usually actually written like this, but I couldn't really find one like that met all the requirements. So, but that means it's a reversible reaction, so it can go either way. So you can have reactants go to products or products go to reactants. And so the other thing you have to remember on this arrow thing, this side is the reactants, the things you put together. The products is what the reaction makes. So that side's the products. All right. So why do we Well, let's get to Antoine Lavoisier, who is apparently thinking about Arby's. Law of conservation of mass. Mass is neither created nor destroyed during ordinary chemical reactions or physical changes. He was the one who sort of well verbalized that. He did it actually to a lot of people thought fire had mass, and he was adamant that that couldn't be true, and he was trying to prove that more than anything. So that was sort of his driving force. So basically, because of the law of conservation of mass, anything on the reactant side of a reaction has to equal the mass of the products. And sometimes if I lit something on fire and weighed it before and after I lit it on fire, it wouldn't have the same weight. But the problem is often it's disappeared into carbon dioxide and water. So if I captured those gases, you would see it did weigh the same. So yeah, phlogiston is, and that's just trivia, the belief that fire had mass. So basically, if you have a reaction and you put it in a sealed tube and mix it up, that tube will weigh the same before as after, or that flask or whatever it is. If it's totally sealed, then because of what Antoine Lavoisier said, the law of conservation of mass, you can't lose any mass from reacting to chemicals and making products, even if the products you think seem lighter, like ash after you burn paper. The reason it's lighter is because the carbon dioxide and the water are left. And if you captured those and kept them all together, you would see that it weighed the same. So we do all of the balancing equations, which is what we're going to get into now. What does it mean to balance an equation? Well, if you have atoms or molecules that react and collide with each other, if there are four blue, right? So on this side we have four blue atoms. We had to have four blue atoms on this side as well. You couldn't have five over here and end up with four. You couldn't have three as a reactant and end up with four. You need to have the same number. And the same is true with these white ones, right? If you have 12 white ones on the left side, you need 12 white ones on the right side. So that's why we balance equations. It's basically because of Antoine Lavoisier. We're trying to satisfy the law of conservation of mass. What's on the reactant side has to equal what's on the product side. So here are the general rules that you have to follow when balancing equations. One, you need to take some inventory. All right, here we had four blue nitrogens, so this side had to have four blue nitrogens. So 4 times 2 there, and 4 times with the 1. That's how we know that was 4. You need to balance by using coefficients and multiply them. Do not change subscripts. So what that means is if I had H2 plus O2 goes to water, I have 2 hydrogens and I have 2 oxygens, and here I have, right, so here I have 2 hydrogens and 2 oxygens, and here I have 2 hydrogens and 1 oxygen. So I can't say, hey, you know what would make this easy? I'm just going to do that, and now I have 2 oxygens. You can't change subscripts. Do not do that. Do not change subscripts. That's going to change the chemical. We learned this already when we were doing compounds. H2O is water. H2O2 is peroxide, hydrogen peroxide. So it's a completely different substance. It's going to do completely different things. So you can't change subscripts. You have to change the numbers in the front if you're going to do this. So that's how you do it. All right. And then make sure coefficients are the lowest possible ratio. So this thing here, these coefficients can actually be reduced. So 6 divided by 2 is 3, 2 divided by 2 is 1, and 4 divided by 2 is 2. So these should actually be 3, 1, 2 in their lowest ratio. That's the last rule. Make sure you have the lowest ratio possible. All right, so let's do some balancing. Here is our first thing. And so the first way I'm going to do this is with, and I can't tell you which one of these ways is going to work for you. It's like asking you, what do you want to drink? Everyone's going to have a different preference. So I'm going to do it a few ways. If you like it, do it that way. If you don't like it, wait till the next one, and maybe that'll work for you. All right, so for this one, I'm going to use dots. So carbon is a black dot, and there's 1 carbon in that, and a methane has 3 hydrogens, or 4 hydrogens, so I'm going to make those blue. So that's methane. Oxygen is O2. So there's 2 dots there. And when you're taking this inventory, you want everything to be the same on both sides of this arrow. So both sides of the reaction arrow. So on this side, I have 1 carbon dioxide, right? So there's 1 carbon there. There's 2 oxygens in that carbon dioxide. And then there's also 1 oxygen here with the water and 2 hydrogens with that oxygen. So, I don't think I used that blue. There we go. All right. So let's take a look at what we have here. On this side, we have 4 hydrogens, right? And on this side, we only have 2 hydrogens. So in order to have those equal, I can't divide this one by 2 because it's CH4. That's the lowest it's going to be. So it's better to multiply that by 2. So making that 2 waters is going to turn this into 4 hydrogens. And it's also going to give me another oxygen. So now I have 4 hydrogens and 4 hydrogens on both sides. That works. I have 1 carbon and 1 carbon on both sides. So let's write that down. Right? I have 1 carbon on this side and I have 1 carbon on this side. So the only problem now is the oxygens. On the right side, I have 2 oxygens plus the other 2 oxygens for a total of 4 oxygens. And on this side, I only have 2 oxygens. So hopefully it makes sense. I'm going to need to multiply that by 2. So now I have 4 oxygens and 4 oxygens, and that's balanced. So 1 methane, 2 oxygen produces 1 carbon dioxide and 2 water. And that's one way to do it, using those dots. So I just did this, but we'll do this another way. So we're going to take inventory in the middle. So here's the middle, right? And so on both sides, we need to take count of oxygen and hydrogen. So on this side, there's 2 hydrogen and there's 2 oxygen. And on this side, there's 2 hydrogen and 1 oxygen. So I guess I'll leave here. Oxygen is a 1 and hydrogen is a 2. So my hydrogens are balanced, but my oxygens aren't. So the only way I'm going to be able to balance my oxygens is by making water happen twice. So if I need to multiply this by 2, that's going to allow me to get 2 oxygens. But in the process, it's also going to give me 2 more hydrogens. So that's a total of 4, right? 2 times 2 is 4 hydrogens, and 2 times the 1 oxygen is 2 oxygens. So now this side is set, this side is not set. I have 2 hydrogens and 2 oxygens. So my oxygens are good, but I need more hydrogen. So the next thing I can do is double this, right? So if I do 2 here, 2 times 2, that gives me 4 hydrogens. The oxygen stays at 2 because there's still a 1 there, right? So that's a 1. So 1 times 2 is 2 oxygens. 2 times 2 is 4 hydrogens. There's 4 hydrogens on both sides. There's 2 oxygens on both sides. That is now balanced. All right. Here's another way to do this. So you see how the SO4 is all together here, and in here it's all together as well. So another way you can do this when you're doing that using the midline, right? Instead of saying sulfur and oxygen, because look how many oxygens there are. There's 4 here, there's 3 in here, there's 12 in here, there's 1 there. You can treat that SO4 as one thing if it's the same on both sides. So if I have an SO4 on this side and I have an SO4 on that side, I can treat it as if it's just one thing. Now, if this confuses you, you don't have to do it. But SO4 on this side, there's 3 of them. And on this side, there's 1 of them. And then let's take a look at our aluminums. I was looking for something more silvery. Do that for aluminum. All right, so on this side, there's 1 aluminum, because that 3 only distributes to the parentheses, right? We talked about that when we were doing formula mass. So it does not go to the aluminum. So there's 1 aluminum on this side. This side has 2 aluminums, because there's a 2 right there as a subscript. So there's that. And then if we look at hydrogens, and oxygens otherwise. So hydrogen-wise, we have 2 hydrogens here and then 3 there. So it's a total of 5 hydrogens on this side. And on this side, we have 2 that are in the water. So that's a bit of a mess. And then our oxygens. So oxygen-wise, because we kept SO4 together, we're only going to look at the oxygens that are in anything but the SO4. So there's 3 oxygens here. And then there's 1 oxygen here because that oxygen's in the SO4. So again, if this doesn't work for you, you can do it the way we've done it in the other 2. You can make the dots or whatever. This is just another way to approach this problem. So first thing I'm going to do, I got my SO4 situation. Let's multiply this by 3 so that I now have 3 SO4s. Okay, so my SO4s are equal. That's also going to give me 6 hydrogens. So 6 hydrogens plus the 3 in here, 6 plus 3 is a total of 9 hydrogens on this side. Okay, aluminum wise, I have 2 on this side, I have 1 on that side, so let's take care of that. Aluminum, I'm going to need to multiply this by 2, which is going to turn that aluminum into 2. So now my aluminums are good. My hydrogens are going to go up again, so 3 times 2 is 6, and then 3 hydrogens times 2 is 6. 6 plus 6 is a total of 12 hydrogens now. So I have 12 hydrogens. Oxygen-wise, I have 3 oxygens times the 2 is a total of 6 oxygens on this side. Okay, and remember these SO4 oxygens are already included in there, so I don't have to worry about those. All right, so then on this side, I'm good with sulfates. I'm good with aluminum. I'm not good with hydrogen, and I'm not good with oxygen. But luckily, all the hydrogen and oxygens that aren't in SO4 all go right here. And since I need 6 oxygens, I'm going to, hopefully that makes sense, I'm going to want to multiply that by 6. That'll turn my oxygens into 6, and it's also going to turn my hydrogens into 12, because I have 6 times 2 hydrogens, 12. So I got 12 and 12, I got 6 and 6, I got 2 and 2, I got 3 and 3, everything works, that is balanced. So I think that next one's not going to fit. So let me discard all that and then continue on to the next one. So now we're looking at, this is a combustion reaction. So I will go back to the dots, I guess, since I've been doing the other way. This has 3 carbons and it has 8 hydrogens. Okay, and then there's 2 oxygens in the middle. And then here's our line of demarcation here, right? And then I have 1 carbon with 2 oxygens there. And then hydrogen with 2 hydrogens with 1 oxygen. All right, so you can see here with all these hydrogens here, I'm going to need a lot more water. And all these carbons here, I'm going to need a lot more carbon dioxide. So let's start with the C3, right? There's 3 here. They all got to go there. So let's multiply the carbon dioxide by 3, because that'll give me the 3 carbons I need. And along with them, it's going to give me a total of 3 times 2, 6 oxygens. So I now have 6 oxygens on this side, and they all came from here, but let's finish up this water here as well. So 8 hydrogens here, they all go here to the 4, to those 2, so it makes sense, hopefully, that I need to multiply this by 4, because 4 times 2 will give me 8 hydrogens, and then each one of those waters needs an oxygen as well. So when I have 4 waters, I have 4 H2Os, right? 1, 2, 3, 4. 4 H2Os. So that's 4 oxygens, 4 plus the 6 here is a total of 10. So I have 10 oxygens on this side. right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My carbons are good. My hydrogens are good. I have 10 oxygens. They all came from this O2, so I need for these to be a total of 10. And if you have a total of 10, it should make sense. That's 1, 2, 3, 4, 5 O2. So this is now balanced. One of these plus 5 of those will give you 3 carbon dioxides and 4 waters. All right. So this is sort of helpful when I was taking nutrition. They would ask you to memorize how many pyruvates you can get from, or pyruvic acids you get from glucose. And because I was a chemist, I knew that since there are 6 carbons here and 3 carbons here, you get twice as many pyruvic acids as you have for every glucose. So every glucose will produce 2 pyruvic acids. You can see that with the oxygens as well, right? 6 oxygens. Hydrogens, it turns out, doesn't work because with water and acidy stuff, they kind of come and go. But I didn't have to memorize how many pyruvic acids you get from glucose because I knew there are 6 carbons in glucose and there's 3 in pyruvic acid. So obviously you would get 2 pyruvic acids for every glucose.